Description of position and orientation of rigid bodies. What we had seen in the last class was that there is a very simple way of describing position and orientation of rigid body associated with transforming position of points on the rigid body to the global frame, and the orientation directions of vectors on the rigid body to the global frame. So what we had seen in the last class was this: the position and orientation of a rigid body is described by the position and orientation of a reference frame attached to the rigid body with respect to the global frame. So the small x, small y, small z are the reference axes of the reference frame attached to the rigid body. The rigid body is not shown there, and the global frame is this capital X, capital Y, capital Z. So the parameters required for transforming vectors and points from the local frame to the global frame are: one, the vector which specifies the position of the origin of the local frame in the global frame. So that particular point let's call P. And the unit vectors associated with the three axes x, small y, and small z expressed in the global frame. The three unit vectors put together as a matrix because that is convenient for transformation. These four vectors, which make up 12 parameters, form the position and orientation of this rigid body with respect to this. That is how we specify that. Now the transformation itself, if you have a point Q on the rigid body, and if it is described by this vector small x q, small y q, small z q in the local frame, its coordinates in the global frame is given by pre-multiplying that with this rotation matrix, which takes vectors from local to global frame, and added to that this particular vector which gives the position of the origin of the local frame and the global frame, that is this vector. So we have essentially 12 parameters for describing position and orientation of rigid bodies. There are other ways of describing this. We will not get into that in detail. What we had started out describing in the last class, at the end of the last class, was the following issue. Suppose we know the position and orientation of one rigid body with respect to another. So second rigid body with respect to the third rigid body with respect to the second, and the second with respect to first, right? I would like to find out the position and orientation of this rigid body with respect to the first, the third with respect to first. Fine. So we had started working out how that can be done, and that is, if you take a point on the third rigid body, let's say the point P, we try to describe that in the first rigid body. If we do that, we get the transformation. So xp, yp, zp in 1 is obtained by the position of this point with respect to this body, that is this vector, plus this vector from, sorry, I made a mistake. We did it slightly differently. We described P with respect to the second rigid body and expressed it in the first rigid body. So the position of the origin of the second rigid body with respect to the first, that is this vector, and the vector from O2, the origin of the second rigid body, to the point P, which is on the third rigid body, that is this vector. Fine. And this particular vector is something we can express in terms of its local coordinates and the position of O3 with respect to O2. So that is what we had done here. This is O2 in 1. This is O2 in 1, that is this particular vector, plus R2 with respect to 1, 2 with respect to 1 into the coordinates of this point in the second rigid body, and then this we expanded, this particular thing we expanded further in this form. That is the origin of the third rigid body with respect to the second plus rotation matrix of 3 with respect to 2 multiplied by the local coordinates of P in 3. Right? Now if we expand this, what we get is, we expand it and collect terms which consists of vectors and matrices multiplying vectors. So O2 in 1 plus so this entire thing I consider to be one vector plus so now I have split it into two vectors. Now I can, if you look at this, you will realize that this consists of two vectors, that is O2 with respect to 1, O2 with respect to 1 plus O3 with respect to 2, but in this coordinate frame. So both of them put together is the vector from O1 to O3, right? The vector O1 to O3 in this reference frame, or rather O3 in this reference frame. So this vector is fine. And this particular, so O3 in this reference frame plus the rotation matrix of this with respect to this, 3 with respect to 1 multiplying the local coordinates of P. That is typically the way we used to write the transformation. So I can call this as R3 with respect to 1 multiplying this local coordinates of, fine. So one thing that emerges from here is the following thing, that is rotation matrix of 3 with respect to 1 is obtained out of multiplication of these two orientation matrices, 2 with respect to 1 post multiplied by 3 with respect to 2, and I can generalize it and write R of some nth reference frame with respect to the first reference frame equals R of 2 with respect to 1, then R of 3 with respect to 2, and so on, and finally R of n with respect to n minus 1. You can, the fact that we can write the orientation of some reference frame with respect to something else using intermediate reference frame, this is very important. This helps us work out orientation or rotation matrices very easily in several cases. Fine. So this is fairly simple. Now a couple of properties of these rotation matrices is something which I wanted to talk about but missed doing last class. I had pointed out the fact that the say local to global, the way we started writing, I'll write. The three columns of this are so the x coordinate, the unit vector in the local x direction in the global frame. Similarly, the unit vector in the local y direction, and then finally the unit vector in the local z direction. Now I said that this is an orthonormal matrix. That is, these columns are orthogonal, mutually orthogonal, and they are normal vectors. They are unit vectors. Fine. Now something very important is the following. What is the rotation matrix of G with respect to L? The global with respect to the local. Obviously that is the inverse of this earlier matrix. It turns out that, and it's fairly easy to show that, this is the same as the transpose of this earlier matrix. So finding inverse is very simple. Just take the transpose. So if you have the rotation matrix from local to global, local with respect to global, then global with respect to local is simply the transpose of that matrix. Now to see that, fine, all you need to do is look at these two reference frames. Let's say global, fine. This particular matrix, 3 by 3 matrix, global with respect to local, has to be, going by the spirit of how we derived local with respect to global, has to be the unit vectors. Columns should be the unit vectors along the global x, y, z axis, right, in the local frame, expressed in the local frame. And if you look at this carefully, you will see that these rows are nothing but that. This is the local coordinates of the global x axis. These are the local coordinates of the global y axis, and these are the local coordinates of the global z axis. That's why this turns out to be the transpose of this. This turns out to be the transpose of this. Fine. So this is something very important which you should keep in mind. Now, we have been using two terms. One, we have been using transformations of vectors and points, and we are calling the associated matrices as orientation matrices or rotation matrices. Rotation involves a displacement. Rotation means a particular type of displacement, right? So how are these two related? This is something that you need to see. The transformations, the meaning of transformations and displacements, and the relation between the two. So if you look at a very simple case in the planar case, let's say this is a global x and y axis, and z axis is out of this plane, and the local xy after a rotation about the z axis is this. Fine. In transformation, what do we do? In transformation, if you take a point P in the local frame, right, that we know its coordinates in the local frame, we find out its coordinates in the global frame, right. So P in some local frame is transformed through a rotation matrix to give you P in the global frame. Fine. Because the origins of the two coordinate frames are coinciding, we don't have a translation here. We don't have a vector of translation here. Now, how is this interpreted as displacement? How do we interpret this as displacement? Fine. In displacement, a displacement operating on a body should displace the body. Fine. So this is a point in the local frame, and you get the coordinates in the global frame in this fashion, but this is for two specific reference frames, right. Now if you regard this rotation, which involved rotation about theta, let's assume, is obtained by angular rotation theta, right. So how do you now interpret this as a rotation? Can be interpreted in this fashion. Imagine, to start with, that these global and local reference frames are coinciding, are parallel. Fine. Take a point P in this. So initially the two bodies are coinciding. Now you rotate the local by this angle theta. Where will P go to? P will go to exactly this particular vector. Fine. So that is how you interpret this as a displacement, in this particular case a pure rotation. Okay. So you can interpret the orientation or rotation matrices and the translating vector, the origin, the position of the origin, as displacements, are specifications of displacements. Fine. So this is another point that you have to keep in mind. Now let me come to a very important question. In order to specify a rotation, we are now using 9 elements. So those are the unit vectors of the local frame. Are all of them required? All the 9 elements. What is the minimum required? 6, 3, 1, none. So let us work it out. I am talking only about orientation. Fine, I am talking only about the orientation matrix or the rotation matrix, which has 9 elements. Fine. So if you look at it closely, you will see that only 3 are required. You can figure it out in the following way. Suppose you know the unit vectors along x and y, z is immediately obtained. How do you obtain it? Cross product of x and y, right? So z is not at all independent, it is simply this. Fine. Now the question of x and y, out of them how many independent elements are there? So x and y are unit vectors, right? They are unit vectors. So if they are unit vectors, each unit vector, how many independent variables are there? So basically 2. It is not very convenient to just use 2 to describe it, but you can do it. Fine. Because it's a unit vector, its magnitude has to be unity. So definitely you can say that the squares of the components have to add up to 1. Correct? So that is a equation which relates the 3 components. So there can only be 2. So let's say x has 2 components. What about y? Y also has 2 components which are independent if you don't consider x. But there is the additional fact that x and y have to be orthogonal. Right? So the components of x, if you square and add, has to be 1. So this is the root of that square. This is 1. So norm of that vector is 1. So that is one relation. Similarly, you have norm of y also as 1. That is another relationship. And finally, x transpose y equals 0. This is 1, by the way. Fine. So how many relations were we able to write? 6 for 9 parameters. Right? So there are only 3 independent elements out of the 9. 3 of them are independent. The rest are all 9 are related by these 6 equations. Fine. So why do we use these 9 elements to represent the orientation? The answer is that it is convenient for doing the transformations. These transformations are things that we would like to do later. But keeping that convenience aside, can we have 3 variables which will give you orientation uniquely without any ambiguity? Well, this was answered by Euler quite a long time back, and he specified various ways of doing this. So we'll see how he described orientation. So there are different types of Euler angles. What we will see are 3, 1, 3 Euler angles. So the way he obtains the rotation matrix or the new position of a body. So let me call this as x1, y1, z1. This is a global frame. Initially, imagine that the local frame is coinciding with the global frame. Fine. And then you rotate the local frame with respect to the global frame about the local z1 axis. Local z axis. Fine. So initially imagine that the local frame is x1, y1, z1. It is coinciding with the global frame. Now I am going to rotate it about the z1 axis to get z2, which is coinciding with z1. x1 would have shifted to x2, y1 would have shifted to y2. Fine. And let these angles of rotation, I am going to specify a sequence of 3 rotations to take the body from initial coincidence with the global frame to its final orientation, alpha, beta and gamma. So this rotation about the z axis is alpha. So angle you see here and here is alpha. Okay. So that is why the first rotation, this is called 3, 1, 3. First about 3, then about 1, which is x, and then again about 3. So next what you do is, the local frame is now at x2, y2, z2. Now rotate the local frame about x2 axis. Fine. If you do that, the new position x3 will be here itself, y3 would have gone somewhere, y2 would go to y3 like this, z2 will go to z3 like this. Fine. And finally a rotation about z3, right? So z4 is the same as this, x3 would go somewhere like this, and y4 so this is the x4, the final orientation of the body, x4, y4, z4 with respect to the original orientation x1, y1, z1. So what we now to do is, we know these 3 angles of rotation, alpha, beta and gamma, about the local z, x and z axis. Now we need to find out this rotation matrix. What is if you look at the coordinate frame, what is the rotation matrix from 4 with respect to 1, right? Now we can use the chain rule of using intermediate coordinate frames in order to express 4 with respect to 1. We can write each of them by themselves are very simple matrices. R12 for example, R2 with respect to 1 for example can be this rotation matrix, which you will get by rotating about the z axis by the amount alpha. What is that? This is something we had derived earlier. This is, if you look at the elements, this is cos alpha minus sin alpha 0, sin alpha cos alpha 0, 0, 0, 1. We had seen this earlier. So the notation R z cap comma alpha is rotation about z cap by amount alpha, right? And alpha, the sense of alpha is in the right hand screw rule. right? When you rotate in the positive direction alpha, positive direction, the screw advances, right hand screw advances towards the tip of the vector. Now what is R3 with respect to 2? In this notation, this rotation matrix obtained by x cap, right? It is rotation about x. This is the second rotation by amount beta. So this you can write as 1 0 0 0 0 cos beta minus sin beta cos beta. Now what about R4 with respect to 3? Right, the same as R rotation about z cap by amount gamma. So substitute in this matrix alpha by gamma. You get the you get the third rotation matrix. So multiply all of them together like this. From alpha, beta and gamma, the Euler angles, 313 Euler angles, you can get the rotation matrix. So if you work it out, you will get the following answer. So I will simply call it the rotation matrix R. You can derive it yourself. Hopefully you will get the following. C alpha means cos alpha. So this is important, so you take it down. The last column is so given the Euler angles, 313 Euler angles, alpha, beta and gamma, you can obtain the rotation matrix. These are the elements of the rotation matrix related to in terms of alpha, beta and gamma. Now an interesting and important question is whether you can get alpha, beta and gamma from the rotation matrix. What are the Euler angles, 313 Euler angles corresponding to a given rotation matrix? So you can do it as an exercise. given R, determine, I'll specify as 313 alpha, beta, gamma. Sorry, alpha, beta, gamma. Fairly easy, one should assume, because there are 9 equations that you can use to get 3 variables, right? 3 unknowns. We have 9 equations. You can equate, yes. So, right, not too much of a problem still. Now this is something we'll do. You can try this out. It is informative to do that. How many number of solutions are there? There are some special cases, but we'll do it in detail in inverse kinematics, because it turns out that precisely this has to be done in inverse kinematics. Fine. Now I mentioned 313. Are there any other possibilities? Yes. So Euler angles really mean this idea of rotating with respect to the local coordinate frame. Every time you shift the local coordinate frame, you rotate with respect to the current local coordinate frame axis. That is the idea Euler used. Fine. So you could have, say, 1, 2, 3 Euler angles. Can you have 1, 1, 1? That will not be very useful. What's quite interesting is that 313 is good enough. You don't have to rotate about the third one, that is y. Right? That's quite interesting. Okay, so you can work out the rotation matrices for 1, 2, 3 or in whatever form they are given. Okay, the basic idea is the same. Yeah, it is. Otherwise, it's a different Euler angle. 3, 2, 1 is different from 1, 2, 3. Right? Okay. Now, why did Euler really go about rotating about these local reference frames? Is it possible to do it with respect to the original global reference frame? It is possible. Only how to derive the rotation matrix, that has to be seen. So we'll try doing that. Now to start with, again we assume, let's say same as Euler angles, let's consider 3 313, or let us have 1, 2, 3. So how do we do the rotation? The idea is this: suppose this is a global reference frame. Initially, the local reference frame is in coincidence with the global reference frame and oriented, aligned in the same directions. So to start with, x, y, z is this. Then you rotate about x axis, 1 is x axis. So this goes to, let's say, a new position, this goes to a new position. Then what do you do? Next, what you do is rotate about this body which is already rotated about this particular axis. Fine, that's what is done. So this small x, y, z, the new positions will go somewhere else, and after that you rotate about the global z axis, that is an axis, and you get the final position. Fine. So if we draw it in a proper way, we will immediately understand in what sequence to rotate what matrices in order to get the rotation matrix. So let me show these axes getting shifted each time. So to I'll use different colors so that things become clear. So to start with, the local frame is coincident with this, but after rotation with respect to about the x axis, this would go to this positions. So the blue, what you see in blue, fine. So let me call this as x dash, y dash, z dash. Now remember that we are going to rotate this whole thing about the y axis. So now what you need to imagine is that, imagine that y dash is fixed with respect to y. Okay, y dash is fixed with respect to, that is, this x dash, y dash, z dash, the frame is fixed with respect to x, y, z, and imagining rotating the frame x, y, z about the y axis. So what we are going to rotate is the frame x, y, z, which you see in black, about the y axis, and when we do this, the blue frame is fixed with respect to the black frame and it moves. Okay, so that is what you need to imagine. Let me show that. So let's assume that this, what I show in red, is the position of the global frame. Now this black frame has rotated. So the black frame has rotated about the y axis. So this is the same as y double dash. Sorry, I should do it in black. Fine. And where did z go? Z went somewhere here, and x dash x went somewhere here. Now along with this black frame, the blue frame has rotated, right? So its relationship with the black frame is the same. So what I show here, this is this x dash, and z dash is this, and y dash is this, right? So x dash, z dash, y dash, x okay, x, y, z. The notations of the frames we have to do carefully. So this is fine. So let me not worry about the notation first. Let me show the various frames in different colors. You can see the colors clearly. Colors are shown as black. Okay, so then I'll have to give notation. So in that shifting, what I'm going to do is I'm keeping the global frame as y, z, then z dash, z dash, x dash, and y dash. So this is a single dash, then y double dash, z double dash, and x double dash. Okay, so the idea is this: look at the relationship between the dash frame and the double dash frame. That's the same as the undashed frame and the dash frame out here. Fine, it's the same as that. And this angle was alpha. So this angle will be alpha. This angle will be alpha. So this is also alpha. So this will also be alpha. Now this is beta. Okay. Now what I do is rotate the whole stuff. Rotate this particular frame x, y, z about the global z direction, and while it rotates, it takes along all the other reference frames as if they are rigidly attached to that. Fine, that is what is important. So if I do that, I get the following. So no point in using color, I suppose. So you have z, y, x. Now you are rotating about this, so you have z dash, you have x dash, so remember what is happening is the following. With each rotation I add a dash to the reference frame. Fine. With each rotation I add a dash to the reference frame. So initially the local frame was aligned with the global frame, and when I rotate, the local frame became x dash, y dash, z dash, and because the rotation was about the x dash axis, x dash coincides with x. Now I rotate this whole thing with respect to about the y axis, right? So I add a dash to each of the axes. So this becomes y dash, y double dash, z dash, z double dash, and x dash, x double dash in this frame, in this picture, right? So you have the x, y, z in the global frame. X dash and x double dash coincide, because the second rotation is about, the first rotation is about the x global frame. This is y and y dash coincide, y double dash is the new position. Z dash and z double dash are all different. The third rotation is about the z frame, the global z frame. So z dash and z are the same. You just add a dash to all the reference frames. Okay, so if we want to look at exactly what the rotations have been, this is alpha, This gives you beta, and the last rotation which you just now gave is gamma. Okay. Now if you want to write the rotation matrix, fine, you will find that it is from the dash frame to the undashed frame into the double dash to the single dash to the triple dash to the two dash. And if you, since we have used 1, 2, 3, this is actually the rotation about x axis, this is about y axis, and this is about z. So we have r with respect to x by angle alpha, then r about y by angle beta, and r about z by angle gamma. The sequence is exactly reversed compared to what you have in the Euler rotations. So, any questions about this? You can work it out as we did earlier. These matrices are fairly simple. Yeah. X will have only 3, I suppose, because 1 is coinciding with that. So let me see. Yeah, that is correct. I made a mistake here. What is pointed out was that if you look at this, x double dash and x dash are coinciding. Now you are going to rotate about the z frame, right? So x dash and x double dash remain coincident, only they become x double dash and x triple dash. Whereas when I do it here, I do a new x triple dash axis. This is the same as x triple dash. Fine. So all these reference frames will have only 3 distinct, all these axes will have only 3 distinct positions. Fine, that is correct. You can see it from this picture. No, 1, 2, 3 all are outside, right, of the x vector. Yeah, you can probably draw it a little differently, right? But the basis is understood. What we are doing is we rotate first, then keep the 2 reference frame rigid and rotate with respect to some global frame again. Then keep the 3 reference frames rigid and rotate again with respect to the global frame. This is the way we proceed, and that is why this sequence turned out to be like this. Okay, so we can obtain the rotation matrix given the 1, 2, 3 fixed frame rotations, or in any sequence that you want. Fine. You haven't finished it? Yeah, is there a question? Oh, it's already time. Okay. So I'll just pose one more question which is very important. Any rotation, whether it be this sequence or whether the original rotation matrix is given, the rotation can be obtained out of a single rotation about a specific axis. This particular axis will be different for different orientations or different. So what I am saying is that a body can be brought from any beginning orientation to any final orientation by a single rotation about a specific axis by an appropriate angle, right? So given the rotation matrix, can you find out that axis and the extent of rotation? And the other way, given this axis and the amount of rotation, can you find out the rotation matrix? So this is another way of describing rotations. Fine. So given rotation about an axis, can you find out the rotation matrix? And given the rotation matrix, can you find out the axis and the amount of rotation? So this is something we will briefly touch upon in the next class, before we proceed to discuss how in space mechanisms, the parameters of mechanisms can be described. Thank you.